everybody, it's Mrs. Hofferberth. Let's talk about metallic bonding today. In a metallic solid, your metal atoms are arranged in a crystal lattice. And as a reminder, a crystal lattice is a three-dimensional arrangement of atoms where the atoms are arranged in an orderly fashion. And so I have here an image of a metallic crystal lattice where you can see that the atoms go in all directions, and this is just a tiny piece of what would be a much larger array of atoms. In a pure metal, all of the atoms are identical within your crystal lattice. But if we take and mix in different elements, we get what's called an alloy, which is a solid mixture. There's some options for how this mixture goes down. If you mix in a second element, or a third element, or however many different elements you have, if you mix in another element and the atoms are of similar size, they're going to take the place of your original metal atoms within the crystal lattice. And this is called a substitutional alloy. On the other hand, if the material you're adding to make your alloy is much smaller in size, so maybe we're taking carbon and we're adding that to iron to make carbon steel. In this case, those much smaller atoms are going to fit into the gaps in the crystal lattice between the original metal atoms, and you'll get what's called an interstitial alloy. And of course, you can do both. You can also have a substitutional alloy with some interstitial alloy in there as well. When you make an alloy, you change the characteristics of the metal itself. Oftentimes, we make alloys in order to make things or metals harder, to change their temperature characteristics, their conductivity characteristics, a whole host of things. And you're familiar with alloys, things like stainless steel, sterling silver, rose gold. All of these are mixtures of atoms and mixtures of metals that are alloys. The question must be asked, how do these metal atoms stay together as a solid? What's holding them together? With all the bonding we've talked about up to this point, we've always had a positive-negative attraction that resulted in a bonding interaction. The same thing is true here. We're going to look at two different ways of considering the bonding in metals. The first is the most simplistic, and this is what you learned in first-year chemistry. We talk about what's called the Electron C model of bonding. In this picture, what we have is we have metals. Let's say we've got magnesium atoms. Their valence electrons for magnesium is going to be in the 3s orbital, and it is 3s2. What we envision happening is that these magnesium atoms lose both of these electrons, and they are donated to an electron C. And all of the atoms, all of the magnesium atoms do this. Well, what you end up with then is the remaining nucleus and inner shell electrons, which as a net will have now a +2 charge since it lost 2 electrons into this electron C. These metal cations will be arranged in the crystal lattice that we just talked about. So imagine that this is three-dimensional because I can't draw in 3 dimensions. And then all of the electrons from all of these different atoms are shared amongst all of the cations. They get involved in what's called delocalized or non-directional bonding, where all of these electrons are attracted to all of the nearby cations that are a result of the magnesium atoms losing or donating these electrons to the electron C. And so you end up with your fabulous electron C, where everything's attracted to everything else. Please note, we still have positive and negative attractions. We have positive metal cations attracted to this negative electron C. The Electron C model does a pretty good job of explaining the general bonding characteristics we're familiar with. Metals conduct electricity. Well, because those electrons are attracted to all of the atoms rather than any particular one, they can move throughout the solid, and that allows for a flow of charged particles. So there's our electrical conduction. Metals are malleable. We can move the atoms relative to one another, and we don't fundamentally change the pattern of what we've got. We still have positive cations attracted to that negative electron C. We've not disrupted the bonding interactions, which allows those atoms to move relative to one another. So that's the malleable and the ductile piece. The fact that these electrons are involved in these non-directional bonds allow them to interact with light, and so metals are shiny. And the fact that metals have a high melting point, well, if you think about melting, you're actually separating your atoms. Pulling your atoms out of the electron C, that's going to be really difficult and it's going to require a very high temperature. So this is a pretty good job of explaining kind of the base properties. It doesn't do an amazing job when you start looking into the nitty-gritty details, things like trends in melting point for atoms, for metals. Those things are not as well explained by this Electron C model. So there must be more, and there is. Okay, we've seen molecular orbital theory before when we talked about covalent bonding. Like we said then, molecular orbital theory is more powerful, but it is also more complicated. So there's pros and cons. Let's consider nickel, kind of just a nice transition metal kicking around here. A single atom of nickel has for its valence an outer layer electrons, an electron configuration of 4s2, 3d8, and then the 4p's are empty. Now I know we usually say that 3d's aren't valence, but they are those last electrons, highest energy electrons. So let's work with these. When you have one nickel atom, this is your electron configuration. Remember when you bring two nickel atoms together and you start forming molecular orbitals, you start forming a series of bonding and anti-bonding orbitals. And every orbital that you mix together, you get an molecular orbital out. If you start imagining having millions and billions and trillions of these atoms in your metallic solid, you pretty quickly get so many molecular orbitals that their energy levels start to overlap, resulting in what we call a band model for understanding. Let's take each of the occupied atomic orbitals and talk about what those molecular orbitals are going to do. So if you have the 4s orbital, those 4s orbitals on all of your adjacent nickels are going to overlap, and they're going to form bonding orbitals and anti-bonding orbitals. And so what I have here in this first rectangle, this is going to be my bonding and anti-bonding orbitals that result from the 4s. Well, the same thing happens with the 4p, which was empty, but those orbitals can still overlap to form molecular orbitals. So you get the same thing going on with the 4p. So that's this box up here. And you also get those 3d orbitals overlapping. Half of them are going to be bonding in character, half of them are going to be anti-bonding in character. So you have all of these molecular orbitals that are available for filling. And so these highest energy level orbitals are all going to take their electrons and dump them into all of these available molecular orbitals. Well, so we're going to fill from the bottom up, just like we always do with all of our bonding stuff. So you're going to start filling the lowest energy orbitals first, and then from there you are going to start filling all the other lowest energy orbitals. These guys are going to get filled from the bottom up. And you're going to fill these orbitals until you run out of electrons. And what you end up with is a lot more bonding orbitals filled than you have anti-bonding orbitals filled. So you end up with an overall bonding interaction because you can take advantage of all of these molecular orbitals that are available. It's interesting because this does help explain things like trends in melting points across the transition metals, where you see melting points rise as you add more electrons to fill your bonding orbitals. And then when your orbitals start to get pretty full, you see those melting points drop off as you start to end up occupying some more of the anti-bonding orbitals. So when this happens, the big takeaway is that all of the highest energy orbitals within your metal atoms overlap to form a whole series of molecular orbitals. And because there's so many of them, because these crystal lattices are huge, you end up with what are effectively like an overlap in terms of energy for those different orbitals. And those are the bands of orbitals. We've got a full band and we've got an empty band of orbitals that are available to be filled or to be involved in other interesting things. This model makes it actually really nice to understand how conductivity happens for metals. You have electrons in these filled molecular orbitals, but there's a whole bunch of empty molecular orbitals that are available, and the difference in energy is negligible. It's very small between your filled and unfilled orbitals. So it's very easy for an electron to be promoted up into what we call the conduction band, or these unfilled molecular orbitals. And an electron, once it's been promoted into those unfilled molecular orbitals, can readily move throughout that crystal lattice.